Alright guys, listen up. Thank you guys in the back for rolling on up here at your leisure. We're going to check FRQs, okay? So you have I saw most of you guys had givens or starting points. Maybe not the final answer, but let's talk about where you got stuck. And I'm going to show you how to grade like AP would, so work with me on like where you get your points. So you don't have a colorful writing device. I'm going to give you one. Anyway, colorful writing devices. The green highlighter. I do like that highlighter, FYI. I have like Sharpies galore. Do I have any other? Here's a pink highlighter. Anybody else? Okay. It might be helpful for you to like annotate where we use different equations or understanding like what the question's truly asking. If it's asking for heat formation or something like that. So I am going to go kind of quickly through this because I have about 20 minutes left with you. Okay. So I'm going through 1, 2, and 3. All right, so what you would expect is, right now, you guys probably assume this, but I have too many FRQs on the test right now, so I'm kind of chopped 1 or 2, because I can't make a choice. But you will see things similar to this, where you are given the data data sets inside the question, and then you're asked to solve for numerous properties of the reaction. So we have all this data, and it says find the standard heat formation. So that's delta HF of butyric acid. So that means for this specific compound here. But we're given some data regarding combustion, right? So we're given the heat of combustion up here as kilojoules per mole, and then there's our combustion equation. So since we're given the heat of combustion, we are going to use that as our heat of reaction total, solving for delta HF of butyric acid. So this is your Big Mama equation for products minus reactants. Give me a thumbs up if you use that. Okay, you should be writing down or give me some feedback, okay, as you go. So you got 1 point for plugging in. You got 1 point for taking your delta H comb, which is your negative 2000 number, and plugging in all the different pieces of water, butyric acid, and the 0 for oxygen. So you had 4 carbon dioxides, 4 waters. You plug those values in separately, and then X was serving as your butyric acid and 0 for the oxygen. So you got 1 point for this whole kind of setup. Yeah. If you didn't write 0, you don't get your extra point. So the first point came from setup, right? The second point came from literally inputting 0. Silly, but once you know the free elements are 0 in terms of delta H. And then final point came from solving mathematically for butyric acid, which to correct sig figs, I'd have to go back and look at this data in a second, but approximately negative 5,330, negative 534 kilojoules per mole. So that's 3 points on A. Thumbs up? What's up, Megan? I get that confused face.
I'm somehow considering like barely the wrong answer.
But barely is not a big deal, okay? We're gonna. That's more than barely. That's like 40 kilojoules. We'll come back to that. Yeah.
Just like you get like 540.
That's fine. Well, I don't really know where you guys are calculating differently because these data points were given to us. Who got this? All right, recheck your calculations, Butterfingers. That's all you. All right, so B asked you to write down the equation for the enthalpy formation. So you're finding butyric acid, a single mole of it, which was a liquid, so you have L, and then you have 4 carbon solids, because carbon is solid in elemental state, 4 diatomic hydrogens and a diatomic oxygen, so those are gaseous, and then at the end you put your delta H that you just got in A. So if you got your wrong delta H in A, but you inputted it in B, you would still get your 1 point for this equation. Yeah? I'm pretty sure if it said thermochemical equation. I don't have the FRQ in front of me. Did it say thermochemical equation? Anybody? If it did, I would say you would not get your credit. Because if it specifically it says for the formation from its elements, no, you would get that point because it doesn't say thermochemical equation, but you should write that down. For C, it said to find the entropy change for this combustion reaction. For the formation equation. My bad, for the formation equation. And you just have to be very careful. You're talking about the combustion, which was the first scenario given, or the formation, which was the second scenario. So that's where some people, I think, went wrong. But on the data table, they gave us all the data points of carbon, oxygen, and hydrogen, which are the pieces we need for the formation equation. So using those data points for the absolute entropy, you're going to plug into the delta H or delta S of formation, which is the total process change, which is still products minus reactants, but we're referencing butyric acid as the product, minus 4 solid carbons, 4 gaseous hydrogen diatomics, and 1 gaseous oxygen. So you got a point for kind of setup, be it just the equation or the actual input data, some form of for setup. Yeah.
So like, even if that was wrong, you just leave it.
Well,
Like,
you put the wrong data in?
If I have the wrong, I just want to put 3C instead of 4Cs.
I am not a genie, but I think you would not get your credit. Because you're, well, did you put 4 in the equation above or put 3 in the equation above?
I just want to put 3 in the equation.
Okay, so then that you would get your point for C because you utilize B and C.
Okay.
Yeah, so you wouldn't get your B point, but you get your C point. There you go. Okay, so in following through, putting in your S values, the total change was negative because we went from gases down to a liquid. So that value should make sense for the delta H because the whole process decreased in entropy. Does that make sense, Megan?
Instead of writing the formation reaction, I took the combustion reaction. So the butyric acid was on the wrong side, and so it ended up being on the other side. Would that be considered?
I would say if it specifically said sulfur S of formation, you wouldn't get your credit because
Well,
you.
I mean, like in the minus reactions.
Did you get, let me look at that in a second, because you used the wrong equation, which is probably not going to give you the point value just because you incorrectly assumed which one to use. Okay, so then lastly, you have to find delta G, and you're using your equation with delta G, delta H, and delta S. So all of these are the formation values specifically for, I don't have the question for me, specifically for the standard free energy of formation of butyric acid. So we're not referring to the combustion equation, we're still referring to B, which is that formation equation. So you're using your S from your formation equation. Notice I went to kilojoules per mole because my delta H that I previously got in oh gosh, A, right, and I have it in B as well, negative 533.9 was in kilojoules per mole. The little knot up here means standard conditions, which means wet in Celsius, 25, so 298 Kelvin, and then plugging in all your values, making sure your units cancel, so kilojoules for me will cancel all the way, kilojoules will be consistent all the way, they're not going to cancel. The Kelvin itself will cancel though. You should end up with about a negative 378 kilojoules per mole. Yeah. Yeah, you can be in joules, it's just like a big number. Like, a lot of times the question will say find delta H in kilojoules per mole. So if it says to do that, then you follow through. Oh, and then you got a point for setting up by inputting the correct delta H and the correct delta S, and then final point for your final answer in the correct units. All right, so I think that was 9 points total. So right home you got out of 9. This is good feedback for you, okay? I'm gonna keep rolling. Okay, so notice that all of these questions are now focusing on thermodynamics, which is our more challenging piece because it brings together a lot of things. Tomorrow I'll talk more about just Q stuff because it's been a while since we did that. All right, so here we are given delta G values for all of the following substances. The bond enthalpy is the same as bond association energies, and then we are asked to find delta H for the reaction using the average bond association energies. So this is different, right? We don't do products minus reactants, we do. So reactants minus products, or bonds broken minus bonds formed. So you had to draw out your structures first, which, given the fact that this is like a organic compound and this is as well, actually I think we did one super similar to that in class. Were you guys comfortable drawing your structures? And if you even have to look it up for now, just make sure you have what you need. But then I think I counted right this time, my carbons. Looking at individually your reactants, I had 1 carbon to carbon, 5 carbon to hydrogens, 1 carbon to chlorine, and 1 chlorine to chlorine bond. And then formation of products, 1 carbon to carbon, 4 carbon to hydrogen, 2 carbon to chlorines, and then 1 H to chlorine. And those were the bonds formed. So I like to make sure I track them, so I do write them all out, and if you're savvy enough to not have to write it all out, kudos to you, but we tend to make mistakes when we don't write down our thought process, especially with like thermochem, because we have a lot of moving variables. So I actually simplified. You don't have to, but I saw the carbon and carbon the same, right? I saw the 5 carbon dihydrogens and 4 carbon dihydrogens, so I simplified from there. That just sometimes helps me if there's a lot going on, because the butterfingers and calculator is just me all day. So if you prefer to do that, you can, just to make sure you're not canceling things that don't cancel. But in the end, once you take your bonds formed minus your bonds broken minus bonds formed, you should get about approximately negative 151 kilojoules per mole. Okay, so you get a point for using the correct equation, right? So somehow showing how you took bonds broken minus bonds formed, and then 1 point for your final answer. So this whole process is endo or exo. Exo, okay, so were the bonds broken, or the bonds formed with more energy? So make a choice. It's one or the other, right? Bonds formed released more energy, so who's more stable, the reactants or the products? The products, right? So these guys released more energy in their formation, so they're much more stable because they released all their enthalpy energy, and these were less stable. So sometimes it's nice to conceptually understand what you're talking about here. The next question asks to solve for delta S of reaction, but you couldn't jump straight into delta S. You actually had to solve for delta G first, because they gave you all the data. Let me scroll back up here for a second. They gave you all the data for delta G. You got delta H from this stuff. So the connection between delta G and delta H is delta S, using the Gibbs-Holtzman, Helmholtz-Holtzman equation. Delta G is equal to delta H minus T delta S. But I wasn't able to plug into that just yet, so I'm going to scroll down here first. I had to solve for delta G first, before it doesn't want to work right now. Okay. So delta G is products minus reactants yet again, and then products minus reactants, when you plug in your HCl, your dichloroethane, and then so forth, you'll have one of each of these, and then a 0 for your chlorine, because it's diatomic free element. So which ones are zeros for thermodynamics? Free elements in which variable? Delta H and delta G, never delta, because the only thing that's 0 in delta S is a perfect crystalline solid. Good. So once you plug in all your data points, you get a negative 115 kilojoules per mole for delta G. That's in kilojoules per mole. My delta H that I just achieved was in kilojoules per mole, and so I decided to keep them in kilojoules per mole for now, plugging them in, solving for X, which is my delta S over here. So mathematically, what do you have to do to isolate delta S? No, I'm not dividing by negative 121. Okay, so I heard subtracting something and then dividing by temperature, right? So you've got to get this by this, you got to get T delta S by itself. So I actually added 151 to the G side and then divided by negative 298 so that you could then isolate delta S. Please do not forget that that's a negative and you're not multiplying those things together. A lot of people make stupid algebra mistakes on stuff like this, which is a shame. And then your total change in entropy is a negative 121 joules per mole K, because I converted it from the kilojoule sense. A lot of times you'll still see delta S as joules. Okay? Questions on the connection between delta G, delta H, all the forms of delta H, just so you know, we can find that in 3 different ways at least, and delta S. Yeah. The T? So what I did, okay, so what I did first, and this is just, you guys can have, like, when is this? Is this algebra 1? You guys have had this like since 8th grade or something. What math are you guys in right now? I know some are calc, some are pre-calc, some are in like crazy maths. Okay, so if I want to isolate delta S over here, I'm gonna have to subtract delta H of reaction. Subtract delta H of reaction. So then I get delta G of reaction minus delta H of reaction equals what? Negative T delta S. So then if I want to solve for delta S, divide by negative T. Negative T. It's no use to try to memorize this, right? Just do the math. Okay. All right, so then the last one, number 3. Oh, sorry, question.
So like, when is G ever going to be positive and how we know?
So you would probably solve for G either doing products minus reactants or this equation. And the way you would absolutely know that G is going to be positive is, one, by solving for it, that's likely going to be a positive H, so endothermic process, and a negative S, which is a decrease in entropy, because those are both two unfavorable conditions for the universe, which would mean delta G would be positive, not thermodynamically favorable. Okay, so not thermodynamically favorable is a positive delta G, thermodynamically favorable is a negative delta G. Okay, last one. Now you with me? Okay, so this was a more cumulative question because you had some what in it? Gas law stuff. So ideal gas law specifically. You had your propane combusting. So the first was write the combustion equation. I did not tell you how many points that last one was. Yeah. Oh, hold off on that for a moment because like I was referencing earlier, this we're going to focus on minimally, but I want you to know that delta G is related to like at least 3 other concepts we're discussing this year. Let me come back to that in a second because I have it on my sticky note, but I didn't scan it like when I scanned this 5 years ago. Okay. All right, so let me hit this first. So you have your combustion equation of propane. So you have a 1 to 5, 3 to 4 ratio, depending on how you write it here. It told you specifically gas and liquid because states of matter and thermo. And after that, so you got 1 point for that equation. And then afterwards, it said find the volume of air. So V at this T, this P, you need to burn 10 grams of the propane, and then assuming that air was only 21% oxygen by volume. So you take your V, air you're looking for. I went ahead and took my 10 grams of propane. When you take your 10 grams of propane, convert it to moles, this is going to give you the relationship now between propane and oxygen, which is the piece that's relevant up here. So for all of this propane to burn, you need basically 5 times as much. So in terms of moles, that's 1.136 moles of oxygen to fully burn all the propane. And then after you plug the N, so the oxygen, which is N, into the ideal gas law, using the temperature and the pressure they gave you, you can solve for oxygen's volume that's needed or required. So that should be about 28 liters, so 28.3 liters of oxygen. But they give you that caveat of percent, so you have to adjust this oxygen volume to be much, much, much higher, because air is not 100% oxygen. So it's not 100% oxygen. I just included one version. You can solve those 2 different ways at least. But if my air is X, my liters of air is X, only 21% of that air is going to be equivalent to what I solved for here, which is about 28 liters. So I need a whole lot of air. I need like 135 liters of air. You also could have done this times, or 1 point, no, that wouldn't work. No, yeah, I divided by 0.21, yeah. I like this one better, actually. Okay, so that was a gas inclusion. Let me scroll back up real fast, okay? Then it told you propane combustion was releasing that amount of energy, calculate the H of formation, given all these variables. So the moment you see HHH, what equation comes to mind? Well, Hess's law of summation, that's summation of equations. Usually, like, you take all your equations and cancel things out. Hess's law, just in general, is products minus reactants. You don't have to know the name of it. Just say delta H of reactions equal to H products minus H reactants. So you have all your data points. You have your H of combustion, which is your total. You had your equation you wrote in A. So if you got the equation wrong in A, but you use the coefficients here, you'd still be getting D or C correct because they are dependent upon each other. So products minus reactants, 0 over there for the oxygen again, Darcy. And you get, you did, okay, so then you get the delta H of formation for propane to be negative 102 kilojoules per mole, 101.1. So you got points for, I didn't show this earlier, but you got points for the correct equation and inputting the correct data, and then a point for your final answer. Okay, last bit, and then we'll talk some more. You guys had, it told you propane burn and there was water surrounding it, and there was energy from the combustion reaction released to the water, something like that, transferred to the water. Yeah, am I right? Is that how that was phrased? So the moment you hear transfer of energy, you should be considering like system and surroundings. So my combustion reaction, which I know is negative because it's an exothermic process releasing energy to the water. So this first kind of thought, or including it some other way down below, switching between negative and positive is important. And so you actually get a point for recognizing that there's heat transfer here. One is a system and one is a surrounding. So that combustion of 30 grams of propane, that's actually not even quite a mole, right? Not quite a mole of propane. So it's not going to release all that energy that you've had initially, which was 2,000 negative, well, releasing 2,220 kilojoules per 1 mole of propane. So you should recognize that this is less because there's not even a full mole to combust here. So this is how much energy is released through the combustion process. So that's why I recognize that as negative Q cohm. And then that amount of energy is transferred to the water, assuming 100% transfer. So that's why I then deemed water as positive. So you just make sure you're really clear on why you're switching signs here. So then after you get to Q of water, you're going to solve for temperature change, so delta T of water. So Q equals MCAT. The Q of water was like 8 kilograms, so that's going to be, need to convert to grams. So I kind of embedded that in my math here. Q over mass times the C of water should give you a total delta T of about 45 degrees Celsius. Okay, so which parts, 1, 2, or 3, which was the more challenging one? 2? Was 2 just because of the K stuff on the end? Oh, okay, okay. So, I didn't want to do the dot cam because the dot cam is evil. So, really quickly on K, what's the equation? Okay, it's right there, thank you. How do you solve for K? Let's rearrange this first. Ln is like natural log. So delta G, a reaction divided by what? Negative RT is equal to ln of K, right? So what's our delta G from that one? Like 151. Negative 115 kilojoules per mole. Right, what's the R? 8.31 what? Joules, right, per mole K. So I already noticed that I have an incongruent unit here. So I'm going to go ahead and take this to what? I'm just going to take it a joule. So 1 kilojoule is 1,000 joules. Okay, so I'm just going to multiply that by 1,000 on top first. And then I'm going to divide by negative 8.314 joules times 298 Kelvin, which is our standard condition. That's why that knot is there. And we get like 0.416. Did we get this far? Those of us who achieved this? Okay. This is equivalent to ln of K. What's the opposite mathematical function of ln? E, right, E. So E caret, so E to the power of 46.416 will cancel out the ln here. So then K is equivalent to 1.44 times 10 to the 20th. It's a high number, right? In general, though, what I want you to glean from this, K has no units, which is kind of nice, with the unit with all the other units we have to deal with. But the one thing I want you to glean is that our delta G was positive or negative. Delta G was positive or negative. Look at the board, guys. It's negative, right? So that means it's thermodynamically favorable in the forward direction. And what I tell you that K had to also be with that case? Greater than 1. Is that greater than 1? Heck yeah, right? Hugely bigger than 1. Okay. Huge. All right, we'll talk about K in more depth later. That's how I'm being concerned. Okay, so we have like 2 minutes left in class. Who's almost done with their lab? All right, good. So I'm not going to ask for the lab to be 100% tomorrow. I'm here for questions after school today. Tomorrow we have like a template picture that you guys can fill in and sit and wait before done with that. But I said 4 and 5 FRQs tomorrow, or do tomorrow, so you can check those. What I'm anticipating in class tomorrow is that we're going to do we're going to do our multiple choice practice, which is in your packet. Okay? Check our multiple choice practice, and then do a soft quiz. and I want to just leave you with this opportunity timed scenario, and then I'll decide what I would do with the grades afterwards, but you really need to, like, you know, put yourself under a time condition so you can practice like you would on the test, okay? Overall, somebody, you know, feel free to text me about which pieces of the puzzle are not fitting. So if it's just Q stuff from way back, Q curves, I mean, go back and look through your notes, Q solutions, Q reactions, stuff like that, okay? If you do want to start your multiple choice early, it's in your packet, you have extra time. Actually, I might have you guys start that when I see you guys again. I know that you guys also have test prep to do tomorrow, unfortunately, so it's kind of too many things in one day. Who's almost on the test prep? Okay. If you are done, you're in the box, right? So I'm here for our 35 minutes of intervention to chat about some of those and if you guys want to start this one. Alright. Honors Chem is getting ready to start gases if you're, you know, wanting some tutoring. Little Boyle's Law action.